going to change gears a little bit from the previous presentations because I think I'm going to be a little bit higher level. But what we wanted to talk about today was ways that we could start to think about helping cities make decisions about where to place sensors inside cities. And this is, of course, a complicated question technically, but also methodologically, but also from a sort of practical policy standpoint. And we're coming at it a little bit more from that sort of practical angle. And this is joint work with Caitlin Robinson, Jack Roberts, and David Herbert. I have to say that the latter two have been pulled off of the project for several months because of COVID research. So what I'm talking about is from pre-pandemic, prehistoric, old times. And this is part of a larger project on spatial inequality in the smart city, which is funded by the Turing Institute. So the big question for today's talk is, how can we help cities and stakeholders make decisions about optimal sensor placement? And I'll probably use the word optimal several times in this presentation, but what we mean by that isn't only sort of from a methodological standpoint, the best possible placement of a given number of sensors within a city, but also thinking about what is best from an inhabitant standpoint, from a policy standpoint, from a city government standpoint, in terms of placing sensors in a way that are representative of different subgroups of the population, being able to justify the choices of sensor locations within cities, making sure that when we develop networks that they're useful. And by this, I'm really referring to the argument that's often made where, say, air pollution is concerned, that it doesn't really matter where the sensors are placed because we're going to model air quality based on the values that are coming out of those sensors, right? Well, we would argue that if what you really want is a good air quality model for a city, then ex post facto, you should probably be thinking about where to put the sensors in order to maximize the fit of the model, right? And then of course we have to think about networks that are cost effective because all of these technologies cost money, maintaining them costs money, right? And our starting point is thinking about where air quality sensors have been placed through the Urban Observatory project in Newcastle. And just a simple observation that if you take Newcastle as a city and you look at where the air quality sensors are, it doesn't at first glance necessarily make sense, right? It would be difficult to come up with a rationale for why the sensors are where they're located. But in fact, it reflects at each increment a deliberate decision to cover particular intersections or particular neighborhoods. But then coming at this from a demographic standpoint, you realize that, well, if you look at the distribution of different subgroups, the location of those sensors isn't necessarily going to be ideal for saying anything about the exposure of those groups. Here we have children in Newcastle, the distribution of those groups relative to measurements of air quality. Okay, so this, of course, when we think about how to place networks, is tied to much bigger questions around urban technologies, smart cities, sensor networks being one example, right? We can think about surveillance and bias, right? Who gets watched? In the case of air quality sensors, we would argue that it's almost the inverse of the typical discourse, where what we really care about is making sure that vulnerable groups are represented in terms of smart city technologies, but also thinking about who technologies are for, ultimately what their purpose is. Is the purpose city branding and being able to say that you have X number of sensors in your city in order to attract investment? Or is it about delivering data that can be used for policy implementation and evaluation? Is it about being able to say something about exposure epidemiologically? These are all very different questions. So what we're at really with this sort of beginning stages of research that I'm talking about today are thinking about designing networks that are not just fit for purpose, but from the very beginning have been organized around being able to answer particular questions. All right. So we can't talk about sensor networks, I think, without talking about trade-offs. And in the case of air quality sensors, which is what I'm going to be talking about today, I tend to think about this in terms of coverage, what share of a population, what share of a city is covered. But an equally justifiable perspective is that what we want is sensors that are covering sources of air pollution, right? So large intersections, places where traffic gets backed up, industrial sources. And given a fit number of sensors, what you would want to do is sort of maximize your coverage of where the pollution is being produced. The inverse of this is to think about it from a demographic standpoint, right? So to think about vulnerable groups. In the case of air quality, who do we need to be able to measure in order to understand who's affected by poor air quality? Right? This is a trickier question in a lot of ways because populations are distributed across space continuously, where we could argue that pollution sources are not. Right? But we're coming at this definitely from the second angle, so thinking about coverage in terms of demographics and vulnerability. But there are other trade-offs, one of which is a very basic one, which is that sensors cost a lot of money. So if you were thinking about trying to help decision makers work through these trade-offs, one of them would be to ask, what is the amount of money that you would like to invest in this? And from there, thinking about maximizing coverage given that fixed budget. But the other trade-offs, of course, are that people sort across space. And so covering, as I'll show you, all of the population doesn't necessarily mean that you'll cover all of the elderly population or all of the young population or all of the poor population. And then I think there's also this important question of visibility and representation, which is almost makes optimizing sensor networks irrelevant, which is that what really matters in terms of political representation and social representation is that different groups of inhabitants in a city can say that they're covered by a sensor network, that they haven't been ignored when these technologies are invested in and located, right? So what I'm going to talk about partly is just tools to help visualize and work through these trade-offs. And these are just wireframes, so sort of just starting to think about how these trade-offs could be visualized in an intuitive way to help policymakers, but thinking about this before sensors are located, okay? So in terms of decision support and the optimization problem that I'll work through at the end of the presentation, we use Newcastle as a case study. We focus on air quality networks, and we're emphasizing demographic coverage, especially vulnerable groups. Right? And so one tricky thing about these trade-offs is that it's not just optimizing location sensors based on one characteristic, that ideally what you're going to be able to do is weight across different dimensions. So for example, this trade-off between pollution source and location of inhabitants. Right? And so what we're thinking about is ways in which we can evaluate multiple criteria at once to come up not necessarily with a best solution, but really to present options to policymakers and users and city inhabitants to be able to say, well, this is why we're choosing the combination of locations that we're choosing, right? So you could think about having a particular budget, being able to walk users through different types of air sensors, what their uses are, how expensive they are, pros and cons, and then basic arithmetic that tells you what you can afford given your preferences. And from there, try to locate the sensors, right? And then multi-weighting, of course, these different criteria. So thinking about point locations, which could be hospitals or schools where vulnerable groups tend to congregate, but also thinking about traffic sources and then social factors. And then I won't touch on this at all, but the fact, as Nick pointed out, that people are moving across space. So looking at where they live or where they work isn't really going to get at this challenge of exposure either, right? So eventually being able to work through that. So I'll spend my remaining time just sort of thinking through some examples of building sensor networks, right? So this is, again, Newcastle's existing network of sensors, but what we want is to take a given number of sensors and a demographic criterion and then locate those sensors sort of as optimally as possible. So we start with a greedy algorithm and a sort of pseudo distance bandwidth that is set to 0.5 kilometer, which easily captures output areas, which are the geographies that we're using, but will extend and capture sort of pieces, fractions of surrounding output areas. What this means is that, practically speaking, when you locate a sensor at the centroid of an output area, you by default capture all of that output area's population and then little bits of the surrounding area. Okay, so what we do is work through locating sensors, up to 60 sensors for different demographic subgroups. And one of the immediate challenges is simply that if you look here on the left, starting with 10 sensors over to the right, up to 30, with just 10 sensors, you can cover, given our criteria, almost 1/4 of the population. By the time you get to 30, you're still only at 40%. And at 60 sensors, you've topped out at about 1/2 of the population. So I think one of the key trade-offs here is simply that if you really want to cover everyone in your city, you're going to need an awful lot of sensors. And of course, most cities can't afford this. And so I think the really challenging piece isn't so much on the method side, but sort of helping individuals and group work through prioritizing where to locate scarce resources, right? But if we then break this down between children and adults, we have sort of the traditional, typical demographic quandary, which is that populations sort over space, right? So deprived populations tend to be clustered. Children tend to be located in some parts of the city, which may be different from where the elderly are located. So how are you going to locate your sensors in such a way that you're trying to cover children and cover the elderly population at the same time? And so this is just sort of showing basically the population density of the total population on the left, children in the middle, and then adults 65 and up on the right. And what this really shows is that on the periphery of the city, where there's lower population density, there's not much value in locating a sensor here, right? You're not going to cover very many people of any type. But if you look at children versus the elderly population, you can see that kids are located in a very particular part of the city, and their geography tends to be a little bit different. It's sort of tricky to capture here, but a little bit different from the elderly population. So you're not going to be able to capture both groups at the same time, all right? And so here, this is just sort of showing the differences in how the algorithm works through in locating the sensors. And it'll run up to 60. In both cases, you top out for children and for the elderly at just over half the population. So it's not that the children, for example, are so clustered that you can cover them very easily, right? And I'm just going to skip through this in the interest of time. And also, it's not that there's so much knowledge that's disclosed at the end, but you can see that it takes a long time to cover a lot of the population, and we're being very generous, right? Half a kilometer for the bandwidth. If you know much about how sensors actually function, is already being sort of generous in terms of how accurate they're likely to be, because they tend to be accurate for relatively small areas, depending on the built environment and the sort of spatial context. So there's this other dilemma of demographic coverage, which I think Nick highlighted really nicely in his presentation, which is that a lot of our analysis looks at residential population. Everything I've shown you so far is where people sleep at night. Now, this is doubly difficult, especially now, because we know that people are mobile, but we know that different types of people are mobile in different ways, right? So workers and children may have much greater activity spaces over the course of the day than the elderly population, but we probably want to be able to say something about exposure to hazardous air quality for lots of different groups. And so one solution is to, well, the easier solution is to look at where we think people are at night and where we think people are during the day. And then the ideal solution would be able to track different types of people over space, so that as they moved in and out of coverage areas of sensors, you were getting a sense of what kinds of people have been exposed to what kind of air quality. Right? But so what we do is locate sensors based on place of work. And here you can see, again, I have 10, 20, and 30 sensors, that it's much easier to cover the working population, because during the day, workers are in many fewer locations than where they are at night, right? The residential population is much more uniformly distributed than the working population. And so with 30 sensors, you can cover over 2/3 of the population on the far right. And this was just sort of a back of the envelope investigation for us, just to sort of see, well, could we do any better? And better, I use very loosely here, than what the Urban Observatory has done, right? In one sense, how do we come out differently if we allow an algorithm to place sensors based on residential coverage, for example? And here with 60 sensors on the right with our algorithm, you see we get much wider coverage across the city of sensors relative to what we have for the Urban Observatory. But of course, the Urban Observatory isn't designed to cover residential locations. That's not the purpose of it. In many cases, as you can see from the sensors located in the middle of the city, it's really about making sure that sources are covered by sensors. But I think this sort of highlights how you could start with the same you could start at the same starting point, right? Cities wanting to locate sensors to measure air quality. And depending on the rules that are used and the decisions are made and how these decisions are weighted, you end up with very different sensor networks that look very different in space. Okay, so just to conclude, I really want to highlight more than something that should be taken for granted. I think that sensors really serve a variety of purposes in cities. For our group, and for probably most of the people watching today, we're thinking about it from sort of the technical, maybe policy standpoint, where it's about measurement and production of data that can be fed into decision-making and policy. But I think that there's a strong argument to be made, especially from the political aspect, about whether people who live in a particular neighborhood look at their street corner and know that they're being represented, right? Know that they're covered by a particular sensor network. And I think there's also the argument to be made that it doesn't really matter what you do with the data, as long as cities can say that they have a certain number of sensors and that they're at the cutting edge of decision making, that serves its own purpose in the larger political context. I would also suggest that modeling isn't a panacea for the demographic coverage problem. That is, the areas that don't have sensors are going to be subject to higher uncertainty. And the way I think about this is that if it really doesn't matter where a given number of sensors is placed, then why are they not placed in the more deprived neighborhoods if it really doesn't matter, right? Why is it that we tend to place them in certain kinds of places? And also, just to make the point, the decision support tools can help with the decision-making process, right? They can help policymakers and users come to a conclusion about where to place sensors, but we're working at this from the perspective of just helping to illustrate sort of the different pathways to making a decision and the different trade-offs that are sometimes sort of underneath the hood in some of these processes. And just to close by saying this is ongoing work. There's still lots to be done. We haven't given too much thought yet to how sensitive our results are to the algorithm choice. We're still working on the decision support interface development. But it's a pleasure to get to share where we are so far with you. And that's it. Thank you.